Welcome to Lithi-Zim. Today's video is hosted by Sage Wagner, a highly skilled geologist and geophysicist who will guide you through the exciting world of geoscience. Join us as we explore Earth.
Seismic waves are waves that travel through the Earth's interior and are caused by natural events such as earthquakes, volcanic eruptions, and landslides. These waves can be used to study the Earth's interior and to locate and measure the magnitude of earthquakes. Global seismology is the study of seismic waves in earthquakes on a global scale, using data from seismographs and other instruments located around the world. Ocean waves and tides are also types of waves, but they occur on the Earth's surface and are caused by the movement of the ocean and the gravitational pull of the Moon and the Sun. Waves are disturbances that move energy through a medium, such as water, air, or the Earth's interior. They do not move matter. Waves are characterized by their wavelength, frequency, and amplitude. There are two main types of waves: spherical waves and plane waves. Spherical waves, also known as radial waves, spread out in all directions from a point source, similar to ripples in a pond. Plane waves, on the other hand, travel in a single direction and maintain a constant shape, like a wave in a calm sea. Waves in spacetime also move energy. This energy is also known as gravitational waves. They are caused by massive objects moving around, like two black holes colliding. A spherical wave is a wave that propagates outward in all directions from a point source, such as a speaker or an explosion. The velocity at which the wave propagates is represented by v. Spherical waves are often sinusoidal, meaning they oscillate at a constant frequency and have a smooth, repetitive shape. As the wave moves away from the source, its amplitude, the height of the wave, decreases. This is known as amplitude decay. This is because the energy of the wave is distributed over an increasing area as the wave expands, resulting in a decrease in the intensity of the wave at any given point. The amplitude decay follows an inverse square law, meaning that the amplitude decreases by a factor of 1, distance squared from the source. A transverse wave, also known as a shear wave, is a type of wave in which the oscillation is perpendicular to the direction of propagation. In two dimensions, the wave can propagate in the x direction and also in a radial direction, originating from a central point. Transverse waves are typically observed in materials that are elastic, such as solids and some liquids. They can be visualized as the movement of particles in the medium perpendicular to the direction of wave propagation. Transverse waves are often used in geophysics, such as studying the Earth's interior and subsurface, to understand the properties of rocks, soils, and other materials. This type of waves are also known as S-waves. Both spring waves and rope waves are examples of mechanical waves, which are waves that propagate through a medium, such as a spring or a rope. These waves are characterized by their wavelength, frequency, and velocity. Both spring and rope waves are propagating the disturbance in the medium to the right at a velocity, known as wave speed. The force that excites the spring wave, A, is perpendicular to the force that excites the rope wave, B. In a spring wave, the compressed and dilated regions of the spring represent where elastic energy is present. The wavelength is defined as the length of one cycle of the wave's compressed and dilated regions. In a rope wave, the wiggle in the rope has peaks and troughs that define the wavelength. At a later time, the wave wiggle's kinetic potential energy has moved forward in the direction of the wave's propagation. It's worth noting that the transverse wave in the rope is different from the longitudinal wave in the spring, as the disturbance in the rope is perpendicular to the direction of propagation, while in the spring is parallel. In a slinky, two types of waves can be observed: P waves and S waves. P waves, also known as primary waves, are longitudinal waves that propagate through a medium by compressing and expanding the material in the direction of wave propagation. S waves, also known as secondary waves, are transverse waves that propagate through a medium by moving the material perpendicular to the direction of wave propagation. Both types of waves can be observed in a slinky and can be distinguished by their different properties. When a disturbance is introduced at one end of the slinky, it will cause the slinky to move in a wave-like motion. The P wave will travel faster than the S wave and will be the first wave to be observed moving through the slinky. The S wave will follow the P wave, moving at a slower velocity. These waves will propagate through the slinky in a one-dimensional fashion, meaning that they will only move in the direction of the slinky and not in the direction perpendicular to it. The waves move in time, meaning that the disturbance will propagate through the slinky in a series of oscillations. Waves have several parameters that describe their properties, including velocity, frequency, period, wavelength, and amplitude. These parameters can be used to understand the behavior of waves and to compare different types of waves. Velocity is the speed at which a wave travels through a medium. Frequency is the number of oscillations that a wave undergoes in a given period of time, measured in Hertz, Hc. Period is the time it takes for one complete oscillation of a wave to occur, measured in seconds. Wavelength is the distance between two consecutive peaks or troughs of a wave, measured in meters. Amplitude is the maximum displacement of a point on a wave from its equilibrium position, measured in meters. Waves can be graphed as a function of time or distance. A single frequency wave will appear as a sine wave in either case. The distance graph shows how the wave oscillates as a function of distance along the medium, from which the wavelength can be determined. The time graph shows how the wave oscillates as a function of time, from which the period and frequency can be obtained. By using both graphs, the wave speed, velocity, can be determined by using the relationship between wa. A longitudinal compressional P wave, also known as primary wave, is a type of mechanical wave that travels through a medium by compressing and expanding the material in the direction of wave propagation. The deformation, or temporary elastic disturbance, propagates through the medium, causing the particles to move in an alternating pattern of compression and dilation, extension. This is known as longitudinal motion, as the particles move parallel to the direction of propagation. The motion of the particles in a P wave can be visualized as a series of compressions and expansions, similar to a slinky when it is pushed and pulled. The material returns to its original shape after the wave passes, meaning that it does not experience any permanent deformation. P waves are faster than S waves and can travel through solids, liquids and gases. P waves are important in seismology as they are the first waves to be recorded in an earthquake, and their velocity and behavior can be used to infer properties of the Earth's interior. This is a description of a transverse wave, also known as a shear wave. In these types of waves, the oscillation is perpendicular to the direction of propagation. The wave is characterized by the movement of particles in the medium perpendicular to the direction of wave propagation. The transverse particle motion can be in any direction, but in the Earth's structure, it's mostly in the vertical, SV, or horizontal, SH, plane. The particle motion is horizontal and perpendicular to the direction of propagation, transverse. To best view the horizontal particle motion, focus on the y-axis, red line, as the wave propagates through it. Amplitude decreases with depth. Material returns to its original shape after the wave passes. The deformation, a temporary elastic disturbance, propagates. Particle motion consists of elliptical motions, generally retrograde elliptical as shown in the figure, in the vertical plane and parallel to the direction of propagation. Amplitude decreases with depth. Material returns to its original shape after the wave passes. This is a description of a love wave, a type of transverse wave that has a horizontal displacement and a vertical velocity. The particle motion is elliptical, and the wave propagates in the horizontal plane. Amplitude decreases with depth, and the material returns to its original shape after the wave passes. Love waves are often observed in seismology and are used to study the Earth's structure and properties. This is a description of a Rayleigh wave, a type of transverse wave that has a horizontal displacement and a vertical velocity. The particle motion is elliptical, and the wave propagates in the horizontal plane. The deformation, or temporary elastic disturbance, is propagated through the medium by the movement of particles in an elliptical pattern. The elliptical motion is generally retrograde, meaning that it rotates in the opposite direction to the wave's propagation. This type of wave is characterized by an amplitude that decreases with depth, and the material returns to its original shape after the wave passes. Love waves are often observed in seismology and are used to study the Earth's structure and properties, specifically in the horizontal plane. Pushing at the spring's end with a force over a distance, work, causes the AB coils to add elastic, compressional, energy. This energy is stored in the spring and is then released as the spring returns to its original shape. This elastic energy then propagates to the right through the spring, in the form of a longitudinal wave. Similarly, pulling the end of the spring back with a force over a distance, work, adds elastic, dilatational, energy to the spring. This energy is also stored in the spring and is released as the spring returns to its original shape. This process also generates a longitudinal wave that propagates to the right through the spring. Both actions, pushing and pulling, generate a P wave, a type of longitudinal wave that travels through the spring compressing and expanding it. A harmonic sinusoidal wave is a type of wave that oscillates in a smooth, repetitive manner, characterized by a single frequency and a constant amplitude. The equation f, x, t, equals a asterisk sin, xt, represents a harmonic sinusoidal wave, where a is the amplitude of the wave and x and t are the space and time coordinates, respectively. This type of wave oscillates up and down across all space and time, meaning it exists everywhere. A space-time localized wave pulse, also known as a pulse wave, is a type of wave that is a superposition of many different frequency components moving in unison, phase. This type of wave is localized in both space and time, meaning it exists at a specific point in space and time and its energy is concentrated in a specific area. The pulse wave can be visualized as a packet of energy that travels through a medium. It is composed of many different frequencies and its amplitude and shape change over time. An explosion creates a force that generates a wave pulse that propagates outwards in time. The wave pulse can be visualized as a series of increasing diameter circles, known as wavefronts, that represent the position of the wave at successively increasing times. Rays are a useful concept in wave theory. They show the path that a parcel of the wavefront travels along. Each ray is always perpendicular to the wavefront and has an arrow to indicate the direction of energy transport. The direction of the ray is the direction in which the wave energy is moving. The wavefront is the set of all points that the wave energy reaches at the same time. Understanding the relationship between wavefronts and rays can help in understanding the behavior and movement of waves. Seismometers are instruments used to measure ground motion, displacement, velocity, and acceleration at the surface. Because space is three-dimensional, seismometers record ground motion in three perpendicular directions: up-down, north-south, and east-west. A seismometer works by hanging a mass from a frame that is attached firmly to the earth, so that the frame moves with the ground motion. The trick of an inertial seismometer is that the inertia of the mass suspended by the spring causes the mass to lag behind the motion of the frame. This causes the mass to be displaced with respect to the frame, and this displacement can be measured by a ruler. In modern systems, the motion is amplified 1,000,000 times. Seismometers are widely used in seismology to study earthquakes and the Earth's structure. They are also used in engineering, mining, and oil exploration to measure ground motion caused by human activities. The information obtained from seismometers is used to understand the behavior and movement of the Earth's crust, to study the internal structure of the Earth, and to predict and mitigate the effects of earthquakes. In a spherical geometry, the distance between 2 points on the Earth's surface is denoted by the angle subtended from the center of the Earth. This is called the epicentral angle, increment. Therefore, in A, all the chords, A1B1, A2B2, etc., have the same epicentral angle. And, if the travel times along each of these chords, seismic ray paths, are the same, this means that the Earth velocity structure only varies with radius, spherically symmetric, and does not vary with azimuth. In B, the same concept applies but for a larger epicentral angle. This means that the distance between the 2 points on the Earth's surface is larger, and therefore the angle subtended from the center of the Earth is also larger. This can be used to study the variations of the Earth's velocity structure with both radius and azimuth, providing more detailed information about the Earth's interior. This concept is widely used in seismology to study the Earth's structure and properties, by analyzing the travel times of seismic waves along different ray paths and comparing them to the expected travel times for a spherically symmetric Earth. The deviation from the expected travel times can provide information about. In around 1920, measurements of travel times from earthquakes at different epicentral angles, distances, were taken and analyzed. The observed time curve showed that at greater distances, the travel times were earlier than would be expected for a uniform velocity Earth. This discovery led to the conclusion that the Earth's velocity increases with depth and is not uniform. Plotting millions of P and S wave travel times from earthquakes allowed scientists to identify different seismic phases. This process of analyzing travel time measurements led to the discovery of the outer liquid iron layer and the solid iron inner core of the Earth. This provided crucial insights into the Earth's internal structure and composition. This technique is widely used in seismology to study the Earth's interior and understand its dynamics. By interpreting the travel time data, scientists are able to infer properties of the Earth's interior such as the speed of seismic waves, density, and temperature. When an incident P wave hits a velocity boundary, it creates 3 P waves: a refracted wave, a transmitted wave, and a reflected wave. Additionally, it also forms a reflected and transmitted S wave. The process of wave propagation at velocity boundaries is described by Snell's law, which states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the ratio of velocities in the two mediums. However, when the outgoing ray is a S wave, the S wave velocity must be used in Snell's law instead of P wave velocity. This is because S waves travel at different velocities than P waves, and the law applies to both types of waves. This understanding of wave propagation helps to better understand and interpret seismic data, and is crucial in the study of the Earth's interior structure and composition. The refraction of a P or S ray due to a velocity change is described by Snell's law. This law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the ratio of velocities in the two mediums. This applies to all types of waves, including seismic waves, light waves, electromagnetic waves, and water waves. The angle between the ray and the interface is always measured with respect to the surface normal. When a ray encounters a velocity contrast, it must refract in order to avoid tearing of the wavefront, which is not physically possible. Additionally, in most cases, a reflected wave is also created. The angle of incidence for a wave reflected from a flat interface is equal to the angle of reflection. This understanding of wave refraction helps to better interpret seismic data and understand the Earth's interior structure and composition. An explosion creates a wave field at a certain point, commonly known as S, and the waves travel outwards as represented by the wavefront at different times. When the wavefront encounters a velocity interface, the waves refract and reflect. The angle at which the waves refract into the rock 2 layer is determined by Snell's law. This law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the ratio of velocities in the two mediums. In other words, the angle of refraction is determined by the relative velocities of the two layers of rock and the angle of incidence. This understanding of wave refraction helps to better interpret seismic data and understand the Earth's interior structure and composition. Snell's law is a mathematical relationship that describes the behavior of waves as they pass through a boundary between two different mediums with different velocities. The law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the ratio of velocities in the two mediums. Mathematically, this can be represented as sin theta 1, sin theta 2 equals v1, v2, where theta 1 is the angle of incidence, theta 2 is the angle of refraction, v1 is the velocity of the wave in the first medium, and v2 is the velocity of the wave in the second medium. The mathematical derivation of Snell's law begins by considering the wavefront of a wave as it passes through a boundary between two mediums. Using the principle of wavefront continuity, it can be shown that the product of the wave's wavelength and frequency must be constant across the boundary. This principle can be used to relate the angle of incidence and angle of refraction to the velocities of the two mediums and the wavelength and frequency of the wave. By using trigonometry, it can be shown that the sine of the angle of incidence is proportional to the component of the wave's velocity that is perpendicular to. Tracing a ray path through multiple layers of the Earth's interior is a simple process that involves using Snell's law sequentially at each successive interface. The angle of incidence, I1, at the top and the bottom, I1, of a layer is the same. If the velocity of the lower layer is greater than that of the upper layer, V2 greater than V1, the ray will refract away from the interface normal. Conversely, if the velocity of the lower layer is lower than that of the upper layer, the ray will refract towards the normal. If the deeper layers have a monotonic increase in velocity, the ray will continue to flatten out with depth. Eventually, the ray will reach its turning depth where it will go exactly horizontal and start to go up. It's important to note that the angle at the top and the bottom of a spherical shell are not the same. This is because the layers are curved. However, if one is just calculating the angles on either side of an interface, the two radius values, r1 and r2, are the same, and the Cartesian form of Snell's law is operative. Representing the Earth's velocity structure as many shells of constant velocity allows for tracing ray paths through the constant velocity shells. Each ray has a different takeoff angle. The changes in the slope, slowness units s per meter, of the travel time curve are directly related to the changes in velocity with depth. The farther the distance a ray travels, the deeper the ray dives before turning around and coming back to the surface. The compressional, bulk, and shear, rigidity, modulus can be derived from P and S wave velocities. The compressional modulus, also known as the bulk modulus, is a measure of a material's resistance to compression. It is defined mathematically as the ratio of the material's change in pressure to its change in volume. The bulk modulus can be calculated from the P wave velocity, Vp, using the following equation. K equals rho v squared P, where rho is the density of the material and Vp is the P wave velocity. The shear modulus, also known as the rigidity modulus, is a measure of a material's resistance to shear stress. It is defined mathematically as the ratio of shear stress to shear strain. The shear modulus can be calculated from the S wave velocity, versus, using the following equation. G equals rho v squared S, where rho is the density of the material and versus is the S wave velocity. By measuring the velocities of P and S waves in a material, it is possible to determine its compressional and shear moduli. These values can be used to infer the material's mechanical properties, such as its stiffness, strength, and deformation behavior. These moduli are fundamental properties of a material and are widely used in the fields of SO. The average radial velocity structure of the Earth is divided into several primary layers, including the crust, mantle lithosphere, upper mantle, transition zone, lower mantle, outer core, and inner core. This information was not known until the 1950s, when scientists began to study the Vp and versus velocity profile of the Earth. The core mantle boundary is the point where the velocity of the waves changes dramatically. The velocity contrast at this boundary is caused by the difference in composition and density between the core and the mantle. The shear velocity of the outer core is zero because the outer core is composed of liquid iron, which does not transmit shear waves. The lack of shear waves in the outer core is a significant factor in determining the structure of the Earth's core. The velocity contrast at the core mantle boundary is a critical factor in understanding the dynamics of the Earth's interior and is used to infer the properties of the core and the mantle.
Thank you for watching. We at Lithi-Zim appreciate your support. It is with great pleasure that we get to bring you these videos about geology, geophysics, GIS, and computer science. Until next time.